Okay, it's a real pleasure to work and live at the biological station for 4 months of the year. Still hard. Maybe it should be turned up a little. I can't get it any closer. And it's just a wonderful experience to have so many people in camp this spring. This spring we have 115 students, but we also have many of you from surrounding communities, and it's always a pleasure to have people come in and visit, talk with us, see what we do, walk our trails, come to our talks, and just be good friends. So thank you. This is our 111th continuous summer. We were founded in 1909, and students and faculty and staff and from the U of M and elsewhere have been coming here ever since. Of course, that sounds like a long time, but it's a very shallow history. In fact, there probably have been people here since the ice sheets were starting to retreat about 12,000 years ago. And we don't know who those people were, but we do know who the people were when European settlers first encountered, traders and settlers first encountered people living in Michigan. Most of those people, especially in this region, were Anishinaabe people. And during a series of treaties from about 1806 to 1836, the year before Michigan became a state, of course, that land was appropriated and taken from them. Many of their descendants live with us today, and we honor their ancestors, and we work closely with our Anishinaabe neighbors and friends to better understand and steward our environment. So we thank them for that. It's also important for us, I think, and particularly for me, to recognize that today, June 6th, is the 75th anniversary of D-Day, when the U.S. joined to resist and eventually defeat an authoritarian and a racist regime, an ideology that threatened peace and stability and justice in the world. This is an all-out effort that required us to act together to meet an existential challenge to civil society, and we did it. Not me, I wasn't there. But I'm the beneficiary of people who did that, and I would like to acknowledge all of them. And it's no overstatement to say that today we face a similarly grave existential crisis. Climate change is something we need to take very seriously. It will change the way we live. It will change how we confront and deal with it and how we survive it and thrive. And there is a path to do that. So that's what I'm going to try to talk about. I'm happy to speak afterward with anybody who would like to talk about it. And I know there are conversations going on all the time. I know that many of you in the audience are working very hard to do just that. I know, for example, that Frank Edwagishik is going to Bonn later this month to a climate change conference. I know others of you are working. I would also like to welcome not only people from surrounding communities, but we have visitors from afar. We have a group of people who are resource managers, foresters, university people from Mexico, Nicaragua, Peru, Honduras, and also Oregon, who are here working with research scientist Luke Nave and John Denial and Brooke. Anyway, a couple of our staff. And they're basically in a course developing standard techniques for measuring carbon in forest soils and wetland soils. So this is a very important thing to do. Nations have to have carbon inventories, and we need skilled people to do that, and we're happy to provide that service in partnership with the U.S. Forest Service. So those are my acknowledgments, and normally we ask someone to introduce a speaker, but I thought it might take too long if someone introduced me, since I had to welcome you all and then come up here and have an introducer and then get introduced. And so I'm going to introduce myself. And it's going to be short because I'm not the object of this talk. My name is Knute Nadelhoffer. If you live in Denmark or Norway or you just like to, you can call me Knute. I'm not Newton, I'm Knute, but Knute works. I got my PhD in 1983 from the University of Wisconsin-Madison. Madison and Wisconsin, of course, are badgers and we're wolverines, and I always tell people they're just different kinds of weasels, so no difference. After I got my PhD, I was a postdoctoral fellow in Woods Hole, Massachusetts at the Marine Biological Laboratory. I'm not a marine biologist, but I worked with a group of biogeochemist and ecosystems ecologist there. Came as a postdoc and I stayed for 20 years. And it wasn't a 20-year postdoc. I left as a senior scientist. So fear not, postdocs. It's hard to capture you for that long. And during that time and through my graduate studies, I studied carbon and nitrogen and nutrient cycling in forest ecosystems and Arctic tundra. So I'm really a person who lives and works north of 40 degrees, not a tropical ecologist, so I'm well suited for the Great Lakes region, I think. And my studies were basically focused on how tundra and forest ecosystems interact with the climate system, how they respond to human impacts, including air pollution and warmer climate. I have served as, I'm not a climate scientist, but I'm an ecologist, biogeochemist who studies the impacts of climate on terrestrial ecosystems. I have served as an expert reviewer on the IPCC 2007 working group on impacts, adaptation, and vulnerability, and I've been working as an expert reviewer on the upcoming IPCC report, special report on climate and land, which should come out near the end of this year, but it's embargoed until then. Also, I've been a member of the U.S. National Climate Assessment Ecosystems Impact Working Group in 2010 and 2012. So I'm in a good position, I think, to talk about this because I've learned about the climate aspect of what I'm going to talk about from my climate scientist colleagues. I'm not a climate scientist, but I know about the feedback and the responses that terrestrial ecosystems have to climate. So that's where we are. So I said all that. So I know at least one person in this audience is familiar with this artist, and he happens to be from Iowa. And his name and his initials are Mark. And if Mark doesn't know, I know Brian Schultens knows. You did. They painted it in a real spot. So who is it?
That window.
Wow. So who's the artist? Grant Wood. And he painted this painting in 1930s called American Gothic. It's an interesting time these people lived in. They had settled on the prairie. Their developers told them that rain would follow the plow, that when they moved to the Great Plains, boy, life was going to be great. Well, this was 1930. About 1933, dust storms started floating up because they plowed everything. And that was a climate impact, but it was also a human-generated tragedy, which was the Dust Bowl. And whenever I look at this picture, I look at the woman on the left, and I think, she doesn't look very happy. She knows something's going on. And I can't tell whether the guy with the pitchfork is just kind of clueless, waiting for something to happen, or saying, let's stop posing for this picture and get to work. I don't know. But I think we have more artists working on climate change today. This is a photo of a painting that I took, it's a photo of a photo that I took at the University of Michigan Museum of Art last weekend. There's a climate change, there's a Art in the Anthropocene exhibit. Has anyone been to it? It's a wonderful exhibit in Ann Arbor. Please go. This is a photo from a Drowning World series by Gideon Mendel, a South African. It's not in South Africa. It happens to be in Surrey, England, but it could fit us in the Midwest. And this is Drowning World by Gideon Mendel, 2014, Experiencing the Anthropocene. So welcome to the Anthropocene. The Anthropocene defines Earth's most recent geologic time period as being human-influenced or anthropogenic. In other words, anthro-human, created by genic. Gene Stormer, a former U of M researcher, is credited with coining this term, but also Paul Crutzen is. So, those guys can duke it out. But I'd like to claim the Michigan person for that. It's named because of overwhelming evidence that atmospheric, geological, hydrologic, biospheric, and other Earth system processes are now strongly altered by humans. And let's take a look at see, I don't know if that works. So this is ice core data. We're going to look at some later. But what I want to point out is this is a 450,000 or so year time scale from nearly 500,000 years ago to the present. The middle line is the Earth's temperature. Now that can be inferred from oxygen isotopes in ice cores. So ice cores in the Antarctic get laid down every year just like tree rings. And they capture samples of the atmosphere. And I can't teach an isotope geochemistry course even though I use isotopes. But oxygen 18 to oxygen 16 ratios can tell you something about the atmosphere and the average temperature of the atmosphere because of the way water forms. So, so the oxygen 18 tells us that, and then here's the temperature deviation from today. Here's today. Okay, our average temperature on Earth is about 57 degrees Fahrenheit, whatever that is in Celsius, but this is degrees Celsius. And if we go back about 12 to 14,000 years, it starts getting cold, and it gets down to minus 8 Celsius. And we have a long period of ice when the glaciers descend upon us, covered us here a couple miles deep. And then 110, 120,000 years ago, we had another warm period, another ice advance. So we've had about 4 or 5 ice advances through this time. And you can see 2 greenhouse gases are bouncing up and down in concert with the temperatures. Now, I don't want to make a lot of that right now, but I'll talk about it in a while. But let's think about this last 100,000 years. Just take a quarter of that last graph. And this is the last glacial cycle. So where were we as human beings? Well, whoops, darn. Okay. There. About 90,000 years ago, the first Homo sapiens, the first fully modern humans, migrated out of Africa. They were preceded by Neanderthals, who were living in Asia and Europe. I'm 3% Neanderthal, so I got there early. That's what 23andMe tells me. So Homo sapiens invaded my people about 90,000 years ago. Of course, I was also Homo sapiens. Anyway, enough of that. Fully modern humans arrived in Australia about 70,000 years ago. So nobody's in North America yet. Migrations of fully modern humans, Homo sapiens, from South Asia migrate to Europe. And then they start interbreeding with Neanderthals, and voila, you have me and many of us in the audience who are here from that. And then about 8,000 or 9,000 years ago, after the glaciers leave, the climate gets stable. And this is what's really interesting. So this is the delta O18. That's the proxy. That's how we can estimate what the temperature is. This is roughly today's temperature. And this is the difference in temperature. So you can see that it was sometimes as low as minus 20 degrees Celsius during the glacial events, but it's, 20 degrees lower than it is from peak temperatures. But up here, we're at about 57 degrees. So we had this remarkably stable period when civilization blossoms on 5 or 6 continents, the Americas, Indian subcontinent, China, Africa, Europe a little bit later. It's called the Holocene, peaceful time, the time of stability. We've had no period in recorded geological history that's as stable as this. And many anthropologists argue that that's why we have cities. That's why we were able to move and develop hierarchical societies, for better or worse, and cities and farms and civilization as we know it in its various forms across the world. Okay. So temperature change from the current value. This time we're going thousands of years ago. I just want to show you one little thing here. This is, again, another representation of where we are today. There's the Holocene, and there is the last 10 or so thousand years after the ices retreat. There's sort of a transition period here where the ice bounces back and forth in Michigan. This is 100,000 years of ice, and then 100,000, almost 120,000 years ago, we had another 20,000-year interglacial. So we're living in an atypical time. But all other things being equal, we probably have about 10,000 years before ice starts coming again. And that'll be another problem, but I don't think we can plan that far in the future. I think we've got to worry about the next 100 or 2. So at the coldest time, that in the last glacial period, it was about 18 degrees Fahrenheit colder, or 10 degrees C colder. There was a warm period in the last interglacial, which, by the way, was much less stable than this interglacial. It was much warmer. Sea levels were much higher. Sea levels went down when water got tied up in ice. And so there actually have been warmer periods in geological history. The thing is, science understands why the temperature goes up and down. I'll talk a little bit about that in a minute. But I usually start my talks like this. I wanted to give you all sort of a broader human background. But I usually shock a lot of people by saying I don't believe in climate change. Because in the sense that, I mean, I believe in it, but I don't believe in it. I don't believe in it as a core belief. If I believed in climate change, I wouldn't need evidence, right? And I think what we sometimes stray away from too often is evidence-based thinking and decision-making. So if I believed in climate change the way I believe that humans are basically good, the way I believe that, well, I don't want to share my personal beliefs, but we have personal beliefs that don't require evidence. Something like climate change requires evidence, either understanding that it exists or understanding it doesn't. But I'm persuaded by decades of research, actually research starting in the 1890s by Svante Arrhenius, Swede, who basically showed with a mathematical physical model that carbon dioxide was a warming gas, and if we burned coal long enough, this was before a lot of oil and gas, that the planet would warm up. But he didn't think it was going to warm up for a couple thousand years because he couldn't imagine how much coal we'd be burning. Anyway, at least 3-4 decades of hard science just build the case for human-caused climate change stronger every month. So we'll look at climate observations, physical processes that are well understood, atmospheric chemistry, the global carbon cycle, and then we'll talk about climate impacts at the global as well as the Great Lakes regional scale. And then solutions, right? There are solutions. That's the good news. So 31 years ago, during a heat wave, Jim Hansen testified before a Senate committee and issued a stark warning. Human-caused global warming was already detectable and would grow far worse with time. What we see on the left is different colors representing departures from a reference point. So this is the temperature anomaly in degrees Fahrenheit based on the 1901 to 2000 baseline. I think that's on 2000 baseline. Anyway, no, that's right. So 1959 to 1988, you can see much of the world wasn't warm on average. Some was a little bit warm, maybe a half degree. A few hot spots. The Arctic is actually heating up faster. By 1988 to 2017, this is what heat looks like on the planet. So this big red area over North America, over the Arctic, is 2.5 to 3 to 4 degrees warmer than the baseline. These are verified by hundreds of thousands of point measurements, satellite measurements. This is the, Hansen was right. I have to quit looking at that thing. I'll look here. The predictions of the world's leading climate scientists have come true with serious consequences for the planet. The lower 48 states since 1988 have warmed at a rate of 5.2 degrees Fahrenheit per century. Now remember what the difference was between cold in the last glacier and today? What was it? Pardon? 18 degrees. So in a century, we got 5 degrees. I mean, that's a lot. Thing is, the rate of warming is increasing, so we're warming faster all the time. The blue line is the trend line, and you can see there's a lot of year-to-year variation. But since 1970, since basically 80, this line is a lot steeper. So the hottest 5 years, as in the satellite record, the hottest 5 years since the late 1800s have all been in the 2010s. So this is 2018. I just downloaded this data yesterday. 2017, 2016, the highest on record. 2015, second highest. 2017, 2018. Why does it matter? This is precipitation in the contiguous U.S. through 2016. So 1900 through 2016, this is 2-day extreme events on 5-year averages. And you can see that starting in about 1960, 1950, we start ramping up in extreme rain events. It's no surprise to climate scientists that we are having extreme rain events all over the Great Lakes and Midwest. We're having floods. Those floods are washing people out of their homes, but they're also washing nutrients and sediments down into our lakes, including the Great Lakes. U.S. Drought Monitor. We all know there have been severe droughts in the West. These are data, and this is the potential. This is what climate change predictions are for fire weather. That is hotter, drier summers, not only in the West, but also in the upper Great Lakes, particularly in our region right here. So these are satellite observations of sea and land surface temperature, and it's basically set up in 10-degree grids, I think, so you can see hot spots around the world. You can see pretty warm spots. You can see sort of warm spots. You can see spots that are near average and a few cold spots. But on average, the Earth is getting warmer. In fact, pulling out that data from the graphical representation I just showed, the 2018 average temperature across the global land and ocean surface was 1.4 degrees above the 20th century average of 57 degrees Fahrenheit. Or you can read the Celsius numbers yourself. This was the 4th highest among all years in the 1880 to 2018 record. And 9 of the 10 top warmest years in the 138 records have occurred since 2010. Another way to look at it. This is the temperature anomaly. That is the deviation from the average of this long base period from 1901 to 2000, basically the 20th century. And this is the global average temperature. 1880, you can see it's lower than the overall average. And we start ramping up in about I like to say 1950 because that's the year I was born, so I'm responsible for all of this. But our global temperatures have gone up about to a maximum about 1.7 degrees Fahrenheit, but let's just call it 1.5 degrees Fahrenheit, or about 0.8 of a degree. That's in 68 years. That's in my lifetime. So how does this happen? Well, I think a lot of you have seen a graph like this. The thing about energy is that the sun produces essentially all the energy we use, but it gives it to us in shortwave radiation, which we don't feel as heat. Heat is when molecules, atoms are moving around, jumping around, and that's heat. So shortwave radiation, some of it's absorbed, some of it's reflected off clouds in the atmosphere, some of it's reflected off the Earth's surface, but the shortwave radiation that's absorbed by the Earth's surface is re-radiated as long-wave radiation or heat. Think about when you were young. Maybe some of you still go barefoot, but if you go barefoot on a black asphalt pavement on a hot summer day, it's hot. Why is it hot? Because that black body is absorbing a lot of shortwave solar radiation, and it's re-emitting it as heat energy or infrared. So that's what happens. Now, the Earth does that, but I'm going to show you a little model. This is a carbon dioxide molecule. So there's a carbon in the middle, and for some reason the 2 oxygen atoms are red. So when shortwave radiation comes in, bounces back as long wave, it excites the atom, makes it move, or the molecule, excuse me, and that generates heat. Doing it again. Okay. I copied that one off the internet, but here's one I made. So oxygen is 2 atoms of oxygen stuck together. Molecule oxygen we breathe, 21% of the Earth's atmosphere. Nitrogen, two nitrogen atoms for a nitrogen molecule. 78% of the Earth's atmosphere. You add those 2 up, and then argon's another 1%. None of these gases that are made of 2-atom molecules absorb heat. But these greenhouse gases: carbon dioxide, 1 carbon, 2 oxygens; nitrous oxide, 2 nitrogens, 1 oxygen. Steve, I hope I got this right. Thank you. There's a chemist. And a methane with a carbon and some hydrogens on it, 4. So notice all these have more than 2 atoms, right? And they all have a shape and a conformation and a stability that allows them to absorb some of the infrared radiation. So infrared has a long band. Each one of these molecules absorbs a different part of that band. So I'm going to show you some infrared radiation coming off the Earth. Whoops, wrong way. I got to start using this thing. So there's the infrared, and it makes them wiggle. And that's heat. So here comes some infrared hitting the oxygen and nitrogen. Goes right through. Doesn't even see it. So when you see these greenhouse gases, carbon dioxide, nitrous oxide, methane, in parts per million or parts per billion, it doesn't really matter that they're parts per billion. It matters how much of it's up there. And there's a lot of it up there. There's over 800 billion metric tons of carbon in the atmosphere as CO2. And that basically can re-radiate a lot of energy. So, I have to say just one other thing. So carbon dioxide is the thing you hear most about. We all talk most about. But methane and nitrous oxide are greenhouse gases at much lower concentrations. But the greenhouse warming potential of methane is 28 to 36 times that of CO2 if you calculate it over 100 years, given the different life spans of these gases. Nitrous oxide, which is basically my favorite element, nitrogen, going up into the air and causing trouble, is 265 to 298 times more powerful than CO2. So we're lucky there's not more of those gases. Still, most of the warming is the result of carbon dioxide, because methane and nitrous oxide are much lower in the atmosphere, but both methane and nitrous oxide add appreciably to the warming potential. So let's look at another representation of how this works. So there's atoms in the air. The Earth's surface absorbs shortwave radiation. It re-radiates long-wave radiation into the atmosphere. So that's the A thing. It's just re-radiating. So it re-radiates in all directions. But some of the infrared heat is absorbed by greenhouse gases like carbon dioxide and re-radiated to space. Some of it just goes to space, misses all the atoms. Some of it is re-radiated back to Earth. Okay? Now, and some makes its way to, I said all that. I talk more, so if you want to read that, you can read it if you understand. All right. Now, with continuing increases in carbon dioxide and other greenhouse gases, more heat will be trapped. It's very, fundamentally, there's a lot of math, but it's pretty simple. These things they absorb infrared radiation, they buzz, they emit heat, they emit radiation, they emit heat, and warm the planet. If we didn't have carbon dioxide in the planetary atmosphere, our average Earth temperature, which is now 57 degrees, would be close to freezing, close to 32. So we rely on it for this stable climate we have, and we rely on the stable composition of the atmosphere to provide a stable planet. So this is just a comparison of what I showed, and we'll move on. The global surface temperature, again, you've seen other representations of this. This is, again, going back to the 1870s to the present, or more or less the present, to about 2015. This is the solar component. So this is the anomaly, again, in degrees Fahrenheit. So look, we've gone from, 0 is the reference point. Whoops. 0 is the reference point. And we basically globally increased our temperature about 1.5 degrees Fahrenheit. The solar anomaly, that is sunspots, has an effect, but notice the scale here. It's an order of magnitude smaller than the scale here. So sunspots have very little effect. Volcanoes, which are often brought into the argument by some, actually have a cooling effect because they emit aerosols into the atmosphere that reflects ultraviolet light back, or not ultraviolet light, but shortwave radiation back into space. So if we look, if we add all these things up, the anthropogenic, or the human-caused component, is basically responsible for everything that we've experienced in the last century. Where does it come from? Well, there's a simple graph. Again, My generation is to blame, 1950. Everything goes haywire. This is total carbon emissions from liquids, which are gas and oil, from solids, which is coal, from natural gas, from cement manufacture, and then from gas flaring. So when methane can't be captured, drillers burn it off and create CO2. So CO2's been increasing since I was in second grade. Well, since before, but David Keeling started measuring carbon dioxide on the top of Mauna Loa Observatory, and many of you know this story, just because he was curious. He wanted to find the cleanest air on the planet, so he goes to the middle of the Pacific Ocean, climbs a high mountain, opens the flasks, shuts it, takes it back, analyzes it for years and years and years, and look what happens. When I was starting graduate school in 1979, we were right here. We increased from about 315 to about somewhere around 330. And we were looking at that around in a seminar once and said, oh, natural cycle, no big deal. It'll probably just do that. And it'll do that. And then by the time we retire, it'll be right there. But it's gone up. From June 1958, when I was sitting in my second grade class, it was 315 parts per million. And this May, it was 415 parts per million on the top of Mauna Loa. Over a 1/3 increase in CO2 in this greenhouse warming gas. There are many more monitoring stations now, so we can get data not going back to the 50s, but to the 80s. And the global average is increased in sort of the same way, a little bit less, because it varies with region on the Earth, but we've gone globally from 338 parts per million in 1980 to 411 parts per million this last year. You can, by the way, I'll make these slides available as PDFs, and you can click on the hyperlinks and get data from these sites. So I'm going to give this presentation away so that you can use it. You can print it out, you can show it to friends, you can steal the slides, I don't care. It's important information. So we'll have it downloadable from the website. So this is, you've heard of the hockey stick? Anybody heard of the hockey stick? Yeah, that's the CO2 curve that goes like this, right? Starts going up in 1950 again. My birth year. And my friends and I call this the hockey team. This is methane is the green. So that's a different scale. You see the CO2 concentration, which is here, it goes from 300, all the way up to way up to almost 400 now, over 400. This graph's a couple years old. Methane concentration is measured again in parts per billion. So that starts at about 600 parts per billion, and it's way more than doubled. Nitrous oxide, the same. So there we go. So another Vostok ice core record. I just have to show this. This is, again, the green rectangles are the warm intervals going from today until almost 500,000 years ago, 5 interglacial cycles. And that, if I superimpose the Mauna Loa curve on that graph, on that time scale, that's what it looks like. That's the Anthropocene. That's the human footprint. That's unexplored territory. That's the danger zone. And we are on track with business as usual to double that by the end of the century. That's that scale inserted. So close to my research is the global carbon cycle. Pre-1900, way before I was born, way before anybody in this room was born, the atmosphere was 280 parts per million, and it had 600 billion metric tons of carbon in the atmosphere as CO2. Okay? Then we started messing with things. The Earth was messing with things before we were. The plants took out, in photosynthesis, about 110 billion metric tons, and respiration by both plants and microbes and soils returned about the same amount. The oceans, because of photosynthesis and dissolved CO2, took up about 90 billion metric tons and released about 90 billion metric tons every year. So all of it's in a pretty close balance until, wham, we start burning fossil fuels and clearing major swaths of forests around the world. And fossil fuel burning is now about 10 billion metric tons of carbon a year. But land use, that is land conversion from forest to pasture, basically contributes about 1.5 billion metric tons. So over 11, maybe 12 billion metric tons are going up into the atmosphere every year. Fortunately, our forests, which we study here at the biological station, are increasing their uptake. But in the meantime, the atmosphere has increased by more than a third to 835 billion metric tons, 411 parts per million. The ocean's taking up more, but that's not good news because that's acidifying the ocean. That's not something I'm going to talk about today, but you may have heard about ocean acidification. It's chemical. It's because there's more carbon dioxide in the water and there's more carbonic acid. So the forests come to the rescue here, though, because they're removing 3 billion metric tons. And so instead of increasing by 11 or 12 billion metric tons per year, the atmosphere is only increasing by 6. Well, that's an ecosystem service. They're helping us out, right? They're buying us some time. And most of that is happening above 30 degrees latitude. So we measure carbon here. That's why our guests are here from Central America and Mexico. We do this all the time. We have a tower, and we'll give tours, a carbon tower that measures the removal of carbon from the atmosphere by our forests. We're part of a network supported so far by the Department of Energy that has these monitoring stations all over the country, and then by other countries all over the world. We're called a Meriflux. We're a Meriflux core site, so a lot of our research is framed by that. Here's another thing, the thermostat, one of the 2 thermostats on the world. So greenhouse gases aside, we've got this wonderful thing called the polar ice cap. There's a wonderful book by emeritus professor from the University of Michigan called A World Without Ice, Henry Pollack. And in that book, he has a quote. He says, "Ice has no point of view. It does not vote. It just melts when the temperature passes 0 degrees C." And that's what it does. Past 30, it does. I mean, it's a fact. And so we're watching, since in the satellite record, since we've had good records of Arctic ice cover since 1979, we're watching this ice cap disappear. This is the September 2018 minimum that I downloaded yesterday. That's the white. I quit pointing at the screen. They're going to see a finger. And the magenta line here is the average from 1979 to 2000 for September. So every summer the ice starts melting, and it reaches its maximum melting point sometime in mid to late September. And then the winter comes and it starts freezing again. So it goes in and out. A September sea ice averaged 4.7 million kilometers squared. This is the 6th lowest ice cover in the 39-year satellite record, about 1.7 million below the 81 to 2010 average. So this area without ice, the area that's blue between the magenta line and the white, is about 11 times Michigan's land area. Get a perspective on that. So that's ocean water that is no longer ice in September. Now, why does that matter? Well, this is another way of representing that satellite record. Early on, in the satellite era, when we were measuring the polar ice coverage, we had about 7.75 million square kilometers. Now the trend line is down to about 4.75. So we've lost 40% of the Arctic ice in the summertime. Why does that matter? Albedo. Not a gang, not a mobster, albedo. It is, some of us probably learned this in science, right? What's albedo? Anybody know? Reflectivity, right. It reflects, and snow and ice reflect more short-wave solar radiation than deep sea, deep green, blue seawater. Sea ice reflects about 30 to 45% of solar radiation, partly because it's rough and it can be, it's not smooth. Snow reflects 40 to 95%. That's over in Greenland. Whereas water only reflects 3 to 10% of solar radiation. The rest of it goes into the water and gets translated into heat, either in the water or transferred back to the atmosphere. So as this polar ice cap disappears, our thermostat disappears. So this is an added climate forcing effect. It's also warming the planet. If you've been listening to the news lately, we're all concerned about the implications for national defense because the Arctic Ocean is now navigable. And there's basically positioning for territory and shipping lanes. I just want, this is from the IPCC earlier report, but people often ask, well, what's the big deal? 1.5, 2 degrees Celsius in a century. Well, it's the rate of warming is increasing, and the next century is going to see more warming than we've seen ever before. But think about a normal distribution of climate. So here's the previous climate. Here's the average temperature. When you have this distribution, you have, the tails are cold and the tails are warm or hot. But when the distribution moves, you have more hot weather, more heat waves, and less cold weather. That affects the whole world, but it really affects us here in Michigan because we have shorter winters with more meltwater, and we have heat waves like everybody else. So it's a cost. I tell people this. I'm a biologist. One of the things that I just more and more upsets me is when global warming is portrayed with a polar bear on a melting ice floe. I mean, I feel for that polar bear, and I understand the importance of it, but climate change, the climate crisis, is affecting all of us. It's affecting our economies. It's affecting our national security. It's affecting our food production systems. It's costing us money. I'm not going to go through all these climate disasters, but we're getting more extreme storms. 14 events. There were 14 billion or more dollar events in 2018, and the cost for those was $91 billion. 16 events in 2017, a more severe year was $306 billion. So this 2-year interval, we've had almost $4 billion worth of climate impact costs. The average cost from 80 to 2018 is $43 billion a year, so it varies year to year. But in more recent years, it's averaging $99 billion a year. So this costs us money. It's money we could be spending on other things, like schools and roads. Downloaded this last night from a site that's still operating. Honestly, when you go to these sites, they're hard to get data off of. I mean, I don't know why. Either people are going in or something. There's maybe a lot of demand overwhelming the system. But this is basically last year's statewide average temperature. So the more orangey sites are much hotter than average. The lighter tan sites are above average, and these numbers are just the rank along this scale here. I think it's kind of a funny way to portray it. And then the Great Plains and Montana are the only states that were not above average. So what does that mean? Well, the average annual temperature for the contiguous U.S. was about 1.5 degrees above the century average in 1 year. 2018 was the 22nd consecutive warmer than average year for the U.S. since 1997. So there are people in this room at the biological station who were born after 1997 who have never experienced an average temperature. Think about that. Last 4-year interval and 5-year interval periods are the warmest 4 and 5-year stretches on record for the contiguous U.S. And since 1985, we said this already, U.S. has increased about 1.5 degrees Fahrenheit, or about 0.8 degrees Celsius per century. So we have choices to make. The IPCC has run a whole bunch of, or compared a whole bunch of models. They don't run models. And this is the temperature change this is the gray or the orange band here is temperature observation since 1900. The modeled historical, there's tons of models that are run, and they all kind of envelope the actual measurements. But the models that go out in the future with business as usual get us up by the end of this century to anywhere from 16 degrees Fahrenheit increase to 8 degrees. Lower emissions, basically roughly equivalent to the Paris Accords, bring the temperature up by about 6 degrees. Now, we had an IPCC special report in December that said 1.5 degrees is what we should try to cap, because otherwise our agricultural systems are going to be damaged. Otherwise, the life as we know it in our civilization is going to change dramatically for the worse. That analysis said we have 12 years to kind of turn this ship around and go in the right direction. So now that we talked about the country and the world, let's talk about the Great Lakes. I've been a science advisor for the Environmental Law and Policy Center, and now I'm on the board. I'm the only scientist on the board, which is kind of scary, because I was telling some friends that believe everything I say. It's very dangerous. But what actually we've done is we've pulled together a large group of scientists from Midwestern universities, right? We're a Midwestern law and policy organization. So we believe that the way to really make a difference is to be a trusted messenger, to really find people in your neighborhood, find people in your circles who are trusted. And Midwest University professors are more trusted than IPCC scientists from Hungary, right? So we pull together groups of scientists to do projects, and this is one. So this is an assessment of the impacts of climate change on the Great Lakes. We completed this before the last election so that any new governors or any new legislators who came in would have the latest information about the Great Lakes. And this is what I'm going to share with you. Also, this report will make downloadable. It's free, right? Everybody who worked on this did it pro bono, their own time. So the Environmental Law and Policy Center with the Chicago Council on Global Affairs commissioned scientists from across the Midwest who were experts mainly on the Great Lakes water body, which is, but also on watersheds. Dr. Don Wobel's good friend, who has actually spoken here in the past, who headed up the last National Climate Assessment, was the lead author on this report. So the temperature in the U.S. states and the Great Lakes has changed by 1.4 degrees for the 1985 to 2016 interval relative to 1901 to 2060. And you can see, where we are on this scale. So the scale, again, goes from 0 on the left to 3.5 degrees. Warmer and warmer colors are hotter and hotter. There we are, right there. We have increased by more than the average. That's us, and that's the Great Lakes Basin. So we've increased by 1.6 degrees Fahrenheit over that period of time. One reason it matters. We have high business as usual scenarios, and we have low scenarios, which are essentially the Paris Accords. These down here in these little graphs show what I showed before, measured values, modeled values. So the modeled temperature for the high scenario, that is business as usual, keep pumping, keep mining, keep burning. This is, well, let's try to remove, let's lower carbon emissions, and this is like, let's really get busy and do everything. Whoops, dangerous. So colors here, the high scenario brings us up 10, 11 degrees by the end of the century. The low scenario, maybe if we're lucky, 4 or 5 degrees. That's a big change. Predicted U.S. precipitation change with the high scenario. Basically, this is a complicated graph, but what I want you to notice is this is more precipitation. The bluer, greener you get, the browner, oranger you get, the drier. Places that are already wet are going to get wetter. Places that are already dry are going to get drier. Talk about reasons for that. Precipitation in the Great Lakes is one of the most amazing things. Is precipitation has gone up by about 10%, but what we're experiencing now is more and more major precipitation events. We get these 2-day downpours, these big floods. They not only flood the rivers, but they move nutrients into the lakes, and they help pollute the lakes and make harmful algal blooms in our estuaries. So, and we have a choice. We can diminish that increase in precipitation and extreme events, or we can just let it go wild. Yeah. So, see, now I see this on the left hand, and I'm using this in the right hand. Why don't I use it in my left hand? I don't know. So these are days with maximum temperatures above 90 are likely to increase significantly under the higher scenario. You can see, and days less than 32 are likely to decrease. Right? So heat waves have health impacts. Total amount of snowfall in the Great Lakes is likely to decrease because our growing seasons are getting shorter and we're getting more punctuated rain events. Lake effect snow might actually increase because we're having less ice cover. But again, that snow melts fast and it gets rained on. So we have these, we're looking at chaotic winters. So one of the interesting things is that summer water temperatures have increased markedly. It's amazing how much. This is the trend. So in Lake Superior, the most rapidly warming and most northerly lake is warming at about 1/2 to 6/10 roughly degree Fahrenheit per year in parts of the lake. Our lake, Michigan, right off of northwestern Michigan, is increasing at about maybe 0.2 to maybe 1/4 degree per year. That's a lot of heat. Water has a high specific heat capacity. So lakes are getting warmer. And this is ice coverage from, again, a NOAA, National Oceanic and Atmospheric Administration data from the Great Lakes Ecological Research Lab. So you can see that ice coverage varies year to year. Some years it's as low as 25%, and some years it's almost 100%, 94%. But let's look at this ice cover. And this is satellite data again. It goes from about 1974 to 2018. That's the long-term average. Those are the number of points in a 23-year period, the first half of this time sequence, where it was below average, 7. After the second half, we have more than twice as many, well, we have twice as many low ice years. So the lakes are warming, there's less ice cover, there's more heat, and the lakes are getting more stratified. In other words, they build up an upper layer and a lower layer. The warm season is longer, it's hotter, so that water stays separated, and we get oxygen depletion in the bottom of the lake and fish deaths. That's what's. This is ice duration. Basically, we're going pretty long, so I'm going to move it fast. Ice cover duration is decreasing across the Great Lakes up to 2.5 days per year in the light areas, and only the near shore areas have no trend, but everything else is pretty much losing at least 1/2 day to 2.5 days a year of ice cover in that period. Great Lakes watershed hydrology, we're experiencing floods, particularly a little west of us, but they're in Michigan too. In fact, they're compromising our coastal town and city combined sewer outfalls, so that when it rains hard, all of a sudden sewage gets mixed with runoff water, and we get huge nutrient inputs into the lake, which then interact with a warmer climate to create algal blooms, microcystis, things we're even seeing in lakes here. So higher summer and fall air temperatures is going to increase evaporation during the growing season, preceded by flooding in the spring, coupled with summer precipitation that's variable and likely lower. So we'll have, this spring is the wettest spring on record for this part of the state. It's likely to be followed by a warm summer. So farmers get into the field late, crops get heat stressed. This reduces production. In fact, changes in seasonal precipitation are affecting farmers. Hotter, drier conditions later in the season, wet early. So it's projected that the temperature and moisture stress will reduce soybean and corn by 10 to 30% by mid-century. Mid-century, by the way, is only like 30 years from now, so not a long time. In the summer, high temperatures and heat waves cause poor air quality. Poor air quality is a threat to human health. People die from it. We don't mention pollen here, but the combination of pollen, higher air temperature, now burning ethanol in the summer in our cars creates more smog. So heat, smog, nitrous oxide, ozone will exacerbate health impacts. So it already has threatened drinking water in many places. So ecology in the Great Lakes. So there's, we've always been experiencing invasive species, largely from global trade and shipping in the Great Lakes. But now the ranges are shifting. The temperature, as the water's warm and the land warms, fish that are adapted towards to warmer climates are moving into the Great Lakes. So game fish like bluegill, smallmouth bass, largemouth bass, brown bullheads have migrated poleward. This kind of increases the diversity in some of our lakes, but it also comes at the expense of growth rates of yellow perch, lake whitefish, and other species that are likely to decrease. Harmful algal blooms, again, the combination of warmer water, more nutrient delivery from farms and combined sewer outfalls to the lakes, creating harmful algal blooms, such as we saw in eastern Lake Erie, or western Lake Erie, but also in estuaries in the north. Talked about that. Lake levels, I didn't show lake levels are the hardest thing to predict, actually. But any changes in the lakes will affect fishing or shipping. likely that irrigation will increase, and that'll affect lake levels, because if we have drier summers, we're going to need to irrigate more. Changing weather and climate conditions put stresses on physical infrastructure, roads, sewers, and it affects the livelihoods of people who rely on hunting, on fishing, forestry, energy, recreation, tourism. So, we're almost done. Policy solutions. What can we do? It's, you know, if you really internalize this stuff, it's kind of hard, you lose sleep at night. We can accelerate the development of renewable resources. And by the way, renewables are getting cheaper and cheaper, faster and faster than we ever thought they would be. We can accelerate the implementation of energy efficiency. So we can revise building codes. So we're building buildings for the 21st century and not the 20th or 19th century. Habits are hard to change. Culture is hard to change. We can accelerate the adoption of electric vehicles that can be provided with power that's produced by wind and solar and other renewable energy rather than coal and oil and gas. And we can develop a more decentralized electricity system based on a more distributed renewable energy. We won't have rolling brownouts if we all have solar and wind power in our counties and regions. We can support national policies to reduce greenhouse gas pollution. We can align our federal and state transportation policies and funding with climate change goals. The University of Michigan is in the we're still in with Paris Climate Accords, as are many states, cities, and towns, and municipal governments. The airline industry has admirably a goal of reducing its carbon emissions by 50% in 30 years. And we can create incentives to decarbonize housing, businesses, and public institutions. Limit agricultural runoff through wise land use, manure management, reducing fertilizer inputs. We can design and develop green infrastructure ranging from wetlands restoration to permeable pavements. There's a lot of work to do. There's a lot to do in a thriving economy that will align itself with renewable energy. This doesn't have to be a lose-win or a lose-lose. It can be a win-win-win situation. And we can restore the proposed $475 million annual federal funding for the Great Lakes Initiative, Great Lakes Restoration Initiative, that has had real impacts on our Great Lakes region. Every year the funding is cut, and then it's been restored every year through work of organizations like the Environmental Law and Policy Center, Natural Resources Defense Council. So overall, our conclusions are, we have a vast and beautiful natural resource, both the lakes themselves and the watersheds and the lands around them. We can't allow them to be degraded through human activities. We're vulnerable. We have 20% of the world's fresh water. Not considering the effects of climate change is not an option. We need our basin to remain healthy, unpolluted, and productive. It's already having an impact, and the impact will increase in the future unless we do something. So, Michigan's future, to summarize. Average annual temperature has increased by about 2 degrees Fahrenheit since the beginning of the 20th century. That's about a half a degree more than the globe. Historically unprecedented future warming is likely. Extreme heat is a particular concern. High temperatures and humidities can cause mortality and morbidity in human populations. Winter and spring precipitation are expected to increase, raising the risk of flooding, which could cause delayed planting and reduced yields. And changes in seasonal and multi-year precipitation, evaporation, temperature can affect water levels in the Great Lakes in ways that we don't quite understand yet. So the things to know about climate change. It refers to long-term shifts in weather conditions. Over most of Earth's history, natural processes have been responsible. We saw that in multiple graphs over the last 500,000 to 100,000 years. But human activity is clearly now the main cause of recent climate change. There is no scientific question or doubt about that any longer. Accumulation of greenhouse gases due to carbon combustion and agriculture is unprecedented. And this evidence is based on fundamental physics, atmospheric chemistry, and intensive measurements of the Earth's climate, the temperature. So, addressing climate change can improve our lives and improve social justice. And I think I'm just going to end it there. I do want to say, well, maybe Yeah. One of the solutions that has been proposed and is to institute what is called a carbon fee and dividend. In other words, we place a price on carbon. Economists agree that we're not going to move fast enough to reduce carbon emissions until we put a price on carbon. Now, new taxes are not palatable to anyone, hardly. But the carbon fee and dividend model is a simple model that's been promoted by a couple of groups. One is called the Citizens Climate Lobby. Carbon fee and dividend puts a dollar amount on every ton of carbon that's mined or extracted or imported. And it takes virtually all that money, 97% of it, and returns it to individual taxpayers. Every citizen in the U.S. would get a share from a carbon fee as a dividend. Now, I'll leave it at that, but there is a bipartisan climate solutions caucus which is considering this as an option. It is equally populated by Democrats and Republicans. In fact, more of our Republicans in Michigan are members than Democratic representatives. So it's time to get all of our congressional representatives on board with bipartisan climate solution strategy.